So far, when we've looked into signals, we looked at voltages or we looked at currents separately. But power electronics is about the multiplication of those two. So a voltage times a current is giving us a power. To transfer the power from a source to an application, from the grid, for example, to any using electronics here, we've got the voltage across the lines here, and we have the current defined as a positive value towards the application and then going back again. Now, once you've defined the direction of a voltage or a current, it is as it is. You can run all the math on it afterwards, and if you figure out, oh, it was supposed to be negative, I defined it the wrong way, that's totally okay. A major disaster would come if you actually change the direction halfway through your calculations and all of a sudden the assumptions that you made, the initial equations that you wrote down about a circuit would not be valid anymore because you're changing the direction of a voltage or a current on the along the way. So I'm defining it as a positive voltage up here. Up here, that's the positive end of a voltage, and that's the negative, even if the value of Vt might be negative in some parts of the time or even all the time. The current is flowing from the left to the right as a positive definition. Furthermore, I assume that both the voltage and the current are sinusoidal. The voltage given by the power plant to provide a sinusoidal voltage here, and then the current I'm also assuming to be sinusoidal here, which would not always be the case, as we've seen already in the rectifier section earlier. Now both of them have a phase phi voltage and phi current, which is respective to the time 0, which I also freely can define when it is. And then they have an amplitude represented by V hat here as the peak value, the amplitude, and the I hat for the time-dependent current. Now, if you multiply 5 and 6, those two equations here, you're getting the instantaneous power, the power at the time t. And it's a bit of a longer derivation here, so I left that one out of the slide here, but you can definitely run the math for yourself. And depending on how you actually write it down at the end, you are getting some parts which are still time dependent, and the rest are going to be constants. So the cosinus, the voltage phase minus the current phase, is a time independent variable. That's something I defined in the beginning, and they will always stay like that. Same for the sine wave down here. The sine of the two phases is time independent, so they can be seen as constants. The amplitudes I took all the way out in front of those square brackets, which is starting here and ending here. And the only time dependency is remaining in what I call A and B. Now looking at the equation inside the curly brackets here, we got that offset of 1, and we're subtracting the cosine from it, and the cosine values can be maximum 1 and minimum -1. If I subtract 1 from 1 here, I get the minimum of the curly bracket equation, so the one I'm calling A here. Minimum value is 0. And if I'm subtracting -1 from 1, then I'm getting actually the maximum, which would be 2 in that case. So the equation A, dependent on time, twice the frequency as the line frequency, the grid, the AC mains frequency, or whatever frequency we got, twice as fast, indicated here by that factor of 2, is going between 0 and 2. Whereas this one down here, the B equation, is a pure sine wave and would alternate between -1 as the minimum of a sine wave and the +1 as the maximum of the sine wave. And then it's inverted by the extra minus sign up here. If we look at that, how that looks is a function of time. It looks like that. The green waveform is an inverted sine wave, and the red waveform is a cosine waveform, also inverted and offset by a factor of 1. Now let's have a look at that in the context of power. A is always positive and B has no DC part. If we look back at our definition of voltage and current, now the A part, which was red, is always a positive direction, so voltage and current multiplied, which is the power, it's always a power transfer from the source to the sink. The B part of the equation, which was green later on, is actually that something that is going back and forth. It can be positive, meaning it's supplying power from the grid towards the application, but it's also going the other way. When it's negative, it's actually reversing the direction of the power flow, and it's bouncing back and forth between the source and the sink, or the load, which it's also called. Now both of them, both the red and the green signal, actually cause losses in those wires here. Now if we also include some resistances in those wires, no conductor would be lossless. You would actually dissipate power in those resistors here. If I'm just indicating the power dissipation through that arrow signal here, you would actually dissipate power in that one. Now there are laws that actually prohibit that the green signal can be too much, because that's actually not contributing anything. It's just bouncing back and forth and generating heat. So it's the overhead in the energy transfer. And you definitely want to maximize the red part. If we're looking a little bit further down the road on the mathematical part of it, and put the A and the B part into its separate definition here. This one up here was the A signal here, and the B signal is appearing down here again, and everything else was outside the equations here. We can define the so-called active power, or the real power, which is transferred to the load. And we got the Q part of it, the reactive power. And the reactive power is the one bouncing back and forth between load and source. There is an interesting analogy to a beer. So if you're pouring a beer, the P part is actually the liquid part. That's what you're drinking. And Q is the foam. And then summing both together, the complex power is actually what's inside your beer glass, the beer plus the foam, but you really want to optimize the stuff that's drinkable and not the white foam on top of it. That leads also to the definition of a power factor. Just as we had the crest factor here, we are relating the real part of the power, the part that we actually want, the desired part, to the total amount of power, the complex power, and that is called the power factor. And in modern power factor applications, and also looking into the laws about those power factors, we are speaking about power factors that are bigger than 95%, sometimes 90%, or even 99%, depending on which application we are speaking about.